So there's that. So was it a Ruben that was just said that they were having some issues? Yeah. So what type of issues are you having with the homework?
Is it due today? It's just the due dates that I had an issue with. The module homework, is that due tonight?
It should be.
Okay.
Yeah, and since I forgot to post homework number 3 last week, I posted it earlier today. So homework 3 is now up there. I believe 4 and 5 are as well. With all those homeworks, you get your 2 weeks to do it. So I guess homework 2 is due today. The lab, um, I kind of, I'm trying to redo some of the material that I've been teaching. And the lab is supposed to be the homework that you're doing right now, and then there's supposed to be another homework, uh, just based on some of the probability stuff. And of course, I forgot to haven't got around to writing that one yet. So I believe if everyone looks online at your grades right now, if you did the intro thing, uh, that is, you should have a grade for that or introduce yourself. Homework number 1, everyone should have a grade, and then I believe for lab 2, everyone's got their 15 points. Because there is no lab 2 yet. Figure it's not your fault I screwed up, so I shouldn't punish you all.
All
I
right.
know it's weird like that, right?
Um,
All right.
I also have another question. I also noticed that our last Zoom wasn't uploaded.
Yeah, I just looked at that and I'll actually show you what's going on because honestly, I screwed this up, or I tend to screw this up every single week. So I'm going to share my screen. So when I go to Zoom, so like I click on the Zoom 1.3 link, blah, 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 click on there. It brings me to here automatically. Then I have to manually go over to cloud recordings, then hit this publish button. If I forget to do that, none of you get to watch the videos, which means none of you get the sleeping aids that you need uh, when you're really stressed out and you need a good night's rest or need to be put into a coma for a little while. So I just hit the publish button, so that should be there. I believe, did I? Kind of hoping that I did all this stuff. So with the YouTube channel, if you go to that, you've got a bunch of the different class things. So the class from last week was actually uploaded to YouTube. Because of course, if I want to download any of these things, I actually have to go through my Zoom and then download it from there. But anyway, should all be up now. And it looks like I'm wearing exactly the same shirt as last week. But I swear I cleaned it. So,
So
any other questions about the homework?
I guess I just have one other question too. From like my understanding of the Zoom or the announcement post that we had another week on this assignment as well. If that's not true, then that's fine. That was what from what my understanding was.
Um, there were a bunch of your classmates that, for whatever reason, couldn't access the Zoom video, so I had to start the YouTube channel. You all get 2 weeks on it. If it takes you a little bit longer than 2 weeks, I'm not gonna mark you down for that. If you try submitting this stuff in the middle or the week between, say, Christmas and New Year, and you expect me to grade it, the answer is no.
So if we
But if it's a couple days late, if it's like a week late and I know that you're working on it, one of your classmates is actually in uh armed services, and they transferred him from one place to another, but then they cut off like his wireless, so he can't log in at the base that he was at or in his barracks or whatever. So he had to go in like an entire week with trying to go to a local cafe in wherever he was stationed in Europe to try to do his homework, try to get all the videos for all of his different classes. So I figure if he can defend the US, I can give him an extra week. And if I'm going to give him an extra week, probably should give all of you the same benefit. So anyway,
Thank you so much. So just so like if I turn it in tomorrow, it won't be late then. Okay.
so
Thank you so much.
no,
We
no,
appreciate
no
you.
problem there. Yeah, on yesterday, I actually gave a talk where we used a little bit of the material that we cover in there. Uh, so for the first homework, let's try and take care of that one during the break. But we've got a couple things to actually talk about today. I was planning on gonna stop the share for a moment. I was actually planning on talking about the normal distribution, the exponential distribution, and then how scientists really screwed up the data when they're looking at the Flint water crisis. But I think that will be a lot better if we do it next week. So you'll get the same material and you'll be able to see everything that's going on, and hopefully uh it won't feel rushed like some of the topics that we've been talking about have felt. Does that make sense? All right. So I need to get my cat off of here because if I flip it over, I'm not sure that the hindquarters here is very entertaining or educational. Oh yeah. Yeah, caught this guy outside of the Starbucks by my house. His first introduction to me was actually him biting me when he was like a 6 week old kitten. His mom had abandoned him and he had infections in both of his eyes and he was just really scrawny and all sorts of stuff. Let's see. It's been a while since I've used this, so I can do that. Uh, well, he was adorable when he was a kitten. Uh, now, I think now he just mostly makes hairballs and then pesters me in the morning to get him food. So we're going to be talking about the normal distribution and the exponential distribution. With both of these are continuous. Which means decimals are actually things that we can have with both of these. Values that we can have with the normal distribution go from negative infinity to positive infinity. With the exponential distribution, they actually start at 0 and go to positive infinity. With the normal distribution, we get to deal with population mean, sample mean, population standard deviation, sample, standard deviation, all sorts of good, clean, fun stuff. With the exponential distribution, basically it just has average. So we already know that the average here, so X bar and the S are the mean and the standard deviation for a sample. Mu and sigma are the mean and standard deviation for a population. For the most part, we will never ever know what these two values are, but instead we will pretend like we do, because if we have a whole lot of data, uh, we will end up having a really good idea what those truly are, hopefully. Uh, when it comes to the standard deviation for the exponential distribution, it's just whatever the average is. One of the reasons why I'm actually covering the exponential distribution, if you have friends that are taking the other stats class with the other professor, I don't think she covers this, is literally because when we do look at the Flint water crisis data, it's exponential, it has an exponential distribution, but the people that were dealing with the data assumed it was normal, decided they were going to force it to be normal. And then when you start telling data what to do, it's kind of like telling a cat what to do. It might listen, but probably not. So we have to be on the watch out for that. With the normal distribution as well, we have what we'd normally consider to be like that bell-shaped curve. And if we're going to be trying to figure out what is the probability of a certain range of values, what we end up doing. So let's say I've got an X high value and an X low value. We'll actually do some of these example problems in a moment. And if anybody doesn't have it already, you can go online and grab that exam one calculator. We will be using both of those tonight, and they'll both be useful for the homework number 4 that I just posted. Well, what we end up doing is we take these high values. Okay, check something real quick. And we create a Z high value. This is basically just going to be X bar minus mu. Then it can be divided by sigma, or sigma divided by the square root of n. And this is going to be that X high value. Z low is going to be X bar low minus the average divided by
What does Z stand for? What is that?
this.
Yeah.
I'll show you in a sec.
Okay.
So once we've got these, we can now actually go and look at our distribution on our normal distribution here. And just because of how it is, Z high is going to be whatever value we find on, say, the right side of whatever it is we're looking for. Z low is going to be the value we find on the left side of whatever it is we're looking for. And just as an example, if we're talking about a 95% confidence interval, the value out here is going to be 1.96. The value out here is going to be negative 1.96. The area that's between these two is going to be that 95%. And then the area in each one of these tails is going to be essentially 2.5%. Let me guess I need to turn this fan off. Sorry. Um, well, I guess that worked. So they don't necessarily have to be symmetric. One of the things that we actually get into a little bit later is we can look at or pretend like we have the normal distribution. So again, we have uh, we try to make every or the average end up being 0. And then we can actually have another thing where we can have another type of 95% confidence interval, but it's this whole area here that's 95%. This area out front is going to be 5%. And for something like this, it's called a one-sided confidence interval. So today we're going to be talking probably way too much about confidence intervals. And part of the idea here, or at least when we're dealing with the normal distribution, there are always things that we can do. Let's say as an example problem, we want to try to figure out what is the probability that some value we're looking for, I'm just going to call that value X, will be between, say, 2 and 7. Where did 2 and 7 come from? I don't know. Just numbers I'm making up. What we need to know here, though, is essentially what is a mu and what is the standard deviation. And if we're looking for, uh, say, one value that's going to fall between there, n is going to be 1. If we want to know what is the average for a group of people going to be that falls between here, then the n value is going to change. So if we have, let's say the average here is 6, standard deviation is 2. What's up, Breck?
Just so so the O with the little line means standard deviation, not sigma.
Yeah. So I think I went over this or should have gone over this on the first day in class, but probably went over it a bit too quickly. But the U with the little tail out in front, that's the mean for population. X bar is going to be mean for a sample. The O with the tail, that's a sigma. And that's the standard deviation for the population. And then if we have S, that the S basically stands for the sigma here, except instead of being in Greek, it's in like English, Romance language letters. But this is going to be the standard deviation for a sample. So
Thank
does
you.
that make a little more sense?
Yes, it does. Thank you.
All right, cool. So if I'm just asking the question, what's the probability that if we know that the population is 6 units, what does the 6 represent? Couldn't care less. If you're a fisherman, or if you like to go fishing, assume that 6 is the average size of a fish in the pond that you're fishing in, or something like that. The standard deviation of 2 pounds is going to be, assuming that we know or we've actually caught all the fish in the pond or something like that. Then we want to ask, what is the probability that based on all of this, you're going to catch a fish that's between 2 and 7 pounds? And if we're only looking at one fish, we can go and we can calculate that. So if you have the exam one calculator out, I think I had this up for some other purposes. But we can actually go to the normal distribution here. Now, Nye said the average is 6. The standard deviation is 2. The high value that we're looking for here is 7. And the low value we're looking for here is 2. So this is telling us that again, assuming that we're looking at the weight of fish in a pond, if the average weight of a fish in that pond is 6 pounds, this is telling us that 66.8% of the time, you are going to catch a fish that is between 2 and 7 pounds. We will do some more calculations like this. But a lot of times I end up just using the normal distribution to help you get an idea about whether or not you, or how much you can actually trust some of the journal articles and stuff like that that you read. So we'll get into that a little bit later. It's not going to let me do that. All right. So one of the other things that comes up, one of the other places where the normal distribution is used a whole lot is actually dealing with IQ scores. One of the weird things that happens with IQ scores is you have a raw score. So I don't know how many points you can have here, but let's say it's 0 to 1,000 or something like that. You figure out what the mean is, and that sets your IQ to 100. The standard deviation is, or the data is manipulated, however, by whatever means are necessary to make sure that the standard deviation is 15. And then we can start asking questions like, what is the probability that you've met someone with an IQ between, say, 70 and 90? So both of these values are actually going to be below average. We can plug our numbers in. So again, if we're just looking for n equals 1, so you can say what's the probability that you meet a single person from a population with an IQ that's a bit below average. So flipping that over to here, I can again say that the average is 100. The standard deviation is 15. The low value in this case is 70. The high value in this case is 90. Oops, got those backwards. So 90 and then 70. So what this is telling you is that if you're just walking down the street and say you see a random person, the probability that they have an IQ that's in the range of 70 to 90 is going to be this 22.974. So I'm just writing on my notes. When n equals 1, we have 0.2297. We can look at this again and say, what happens if n is equal to let's say 9. Go ahead.
Can
And
I,
then,
this might be dumb. Can I have a refresher of what standard deviation is?
okay. Um, so standard deviation is just a measure, or one way that we measure something called spread.
Okay.
Uh, the smaller it is, if we think about this in terms of a confidence interval, and I'll stop the share real quick so we can see what's going on here. So let's say, so if we're dealing with this data, we've got 100, and if we want to create a 95% confidence interval for uh, like say all people, technically, or shouldn't say Z, should put the T value in there. If we're just looking at a pop or some people that we talk to, we'll have the standard deviation square root of n. And essentially, this determines how big that confidence interval is. So if we, the larger this is, the larger the confidence interval is going to be. So if I end up with, say, something like 60 to 140, and that's my 95% confidence interval, we can go back, we can calculate S, see what that's going to be. If the standard deviation is smaller, so there's a lot less variability, the less variability there is, if we're talking about, uh, like if we're talking about a manufacturing process, if the variability is too large, uh, a plant might start rejecting products that your company makes. If the variability on this is too large, uh, so if we're talking about, say, battery life for your pacemaker, uh, something like that, there could be issues if they have to go in and say replace the battery every 3 months on your pacemaker versus every, say, 4 years, something like that. If we and if we look at two sets of data here, let's say from here to here with one data set is 2 standard deviations. What is that number right now? I'm not going to say anything. Well, we might have another data set that looks more like that. And on this one from here to say here would be that same 2 sigma. As far as data goes, the smaller the standard deviation is, the better it is for trying to predict what's going to happen. Because if I say something like, hey, like the balance of my stock portfolio or something like that, let's say it's $100,000. And if I have something, or if I have all that money put into um, really, why am I having an issue trying to think of the word right now? But if I have that put into really risky stocks, say by the time I retire, I could have somewhere between $0 and I know this isn't going to necessarily be symmetric, but let's say $1.2 million. If I put that same amount of money into stock that isn't as risky, I might be able to guarantee myself that I'll have, say, 800,000 to $900,000 when I retire. So larger the variability, the harder it is to predict, the more risk there's going to be in whatever it is you're doing. Uh, the more risk there is, the greater the chances that, like in this case, that you can have absolute failure. Um, so if just out of curiosity, if you had one of these two stock portfolios, and with one of them you could have anywhere between 0 and 1.2 million in retirement versus another portfolio you're guaranteed or almost guaranteed to have 800,000 to 900,000. Which of these portfolios would you rather have, A or B? Yeah. Yeah.
B.
So, uh, in statistics, we use the standard deviation a lot to help us create accurate predictions. Um, and with A, what if instead of 1.2, what if you could have somewhere between 0 and $2 million? Does that change anyone's opinion? And some of the stuff that we talk about in here, when it does come to these types of risk, it literally depends on, there is no, say, correct answer. It's, did you make the decision based on all the data that was available? You have no idea what the outcome is going to be. You won't know what the outcome is going to be until it happens. But as long as you made your decision based on the best information you could have had at the time, that's what actually makes a decision good, at least as far as stats goes. But anyway, so we've got uh, or we can look at these different things here. The one on the bottom has a lot less risk involved in it, but on average, up here, this is going to give you, if we're looking at $2 million, on average, this is going to have $1 million for you. This is going to have 850,000. You might be completely broke up here. You might have as much as 2 million, but down here, you've got something that you can actually plan with, right? I don't know how old anyone is. But let's say you're 25 right now. And if you're trying to plan for retirement, would you rather be able to plan on having 800, say 800 and $900,000 to retire on, or somewhere between 0 and 2 million? You've all basically already answered that. Personally, I'd rather be in this group. This allows you to start thinking about, say, in stats, we'd call it forecasting, but for regular human beings, you can consider it thinking about the future. So if you're not sure if you're going to have any money in retirement versus say 2 million, and then have to and then get say Social Security versus 800 to 900,000 and then get Social Security. You can start planning perhaps instead of thinking about, oh, I'm going to go and try, or when I retire, yeah, that's when I'll buy my Ferrari because I'll have a couple million in the bank, whatever. You can start planning for your future. You can start getting an idea. Do you really want to be, if you're thinking about starting a family, do you really want to have a family now and then when you retire have a 5,000 square foot, 14 bedroom home with 19 bathrooms and so on? Or would you rather be looking at, say, 1,000 to 2,000 square foot, 3 bedroom, 2 bath, something like that? So with the variability, the larger it is, the harder it is to plan for the future. Uh, the wider the variety of responses you could actually get. And if we're talking about, we're going to get into this later on. We think about, or later on, we're going to think about the standard deviation as being noise. And a lot of statistics is about trying to deal with the signal versus the noise. So the louder the noise is, the bigger the standard deviation, the bigger the standard deviation, the harder it is to kind of get an idea about what's going on, the harder it is to get an idea about what's going on, the harder it is to make decisions, the harder it is to make decisions, the more likely you are to put off making those decisions. So, uh, again, with the standard deviation, it's just a measure of spread. It measures how far from the average we can kind of predict the values we're going to get are going to be. Does that make sense? Or did I just ramble on way, way too much?
Sort of. It
So,
sort of made sense.
yeah. Well, we'll actually look at a couple things where we look at uh we'll look at some of these problems using IQ, and you can kind of get an idea or see what the variability does. We can look again at risk and stocks and stuff like that. Most of the time I use standard deviation or something called standard error with uh, confidence intervals, and we're going to do a bunch of calculations on that. So we'll be using it quite a bit. And one of the other things that comes up is if you're trying to later on in the class, for those of you that had stats already, we're going to be getting into hypothesis testing. And with hypothesis testing, we're trying to figure out say, these two groups the same or are they different? The smaller the standard deviation is, the better the chances we're going to see whether there truly is a difference between those two groups. So, there have actually been some experiments that I've actually participated in where because of the way things were designed, there was a lot of extra variability that was not accounted for. It was assumed you can't do anything with it. So when you look at the results, and this was for a toxicology experiment that I was working on, you couldn't tell if this particular chemical we were looking at was toxic or not. But when I went and looked at some of the data, saw what was going on, did a better analysis than what the toxicologists were doing. We were able to take into account a lot of the other factors and then get a really, really uh, precise or a much more precise answer to is this chemical toxic, yes or no? Way to think about it too, and I think some of you actually brought this stuff up a couple of weeks ago when we're talking about cancer. If I just ask you straight up, what are the chances or what's the probability that any one of us has cancer? When we looked that up, we found that ended up being about, I think in like Oakland County is 350 people have cancer per 100,000 residents. So percentage wise, that's 0.35% of all residents of Oakland County currently have cancer. And then I believe some of you rightly said, well, what if you're a smoker? Okay. Uh, we can look at those numbers and get a much better idea about what your particular cancer rate is based on if you're a smoker. If we know that you're, say, a smoker and you're a little bit older person, by adding in all these other things, we're taking a guess that goes from like this, say, down to something like that. So, one of the nicer things about what we do later on is we can actually take into account pretty much anything that you want to consider and come up with a very specific probability that, say, you in particular, if it's of your interest, uh, say, currently have cancer, and potentially look at the data the way that we're going to look at it and try to come up with a way of predicting, say, what type of cancer are you going to get, when are you going to get that cancer, and so on. If we have a very large variability in the data, very large standard deviation, that's going to make all those predictions. Yeah, there's somewhere between a 0 and 100% chance you'll have cancer. And it's probably going to happen somewhere between 0 and 100 years of life. Does that help anyone predict and make plans for the future? Whereas if I can, uh, like, if say you are interested in breast cancer because it does run in your family, we can take your genetics, we can look at a lot of other stuff and come up with a prediction. Are you going to have cancer, say, by the time you're 50, by the time you're 60, by the time you're 70, something like that? So the bigger the standard deviation, the worse it is uh, for pretty much everything that we want to do. And some of the stuff, it does get a bit weirder than that. Just gonna just gonna let you know. So I'm gonna flip this back over. So I was saying we can look at this and we can look at what's up, Brooke?
So, but even like when all of our data is changing, we're still assuming that um it's 95 of the CI, correct?
Well, we'll actually get into that the second part of class.
Okay.
And don't tell anyone. But right now I'm actually teaching a business stats class, and it's a business stats 2 class, which mean for them, pretty much everything that you're going to learn in this class, they get it, and you have 15 weeks to learn it. They actually get 30 weeks. So with the other class that I'm teaching, it's the last half of our class, but because everything is so like spread out, we get to do a whole lot more examples, and I'll let you all watch those videos if you want to, because I know some of the stuff, it does go by really quickly, and there are some times when I'm looking at the time and trying to think, oh my God, oh my God, oh my God, I need to talk about this and this and this and this and this, so I have to go really quickly. But with that class, it's basically the second half of class, but over a 15-week period instead of 7.
Why is that?
So we talk about that, but to answer your question really quickly, the recommendation that I gave the students in that class is if you have small sample sizes, and then what does small mean? And small is honestly a relative term. But if we have, say, we're looking at the average of 10 people, 15, 20 people, something like that, I would probably actually go with a 90% confidence interval. If I'm looking at the average of, say, 200,000, 300,000 people, I would actually go with a 99% confidence interval. Uh, and there are some reasons for that that we'll actually get into later. And some of it, we'll hint at it tonight.
Okay,
Okay?
thank you.
Yeah, no problem. So we're going to flip this over again. So if we're looking at say this n equals 9 thing. So we can ask the question, up here we ask the question, what is the probability that if you're just walking down the street and you meet one person on the street, their IQ is going to be between 70 and 90. So we got that at about 23%. When we look at, say, n equals 9, that means what is the probability that if we're walking down the street and we see a group of, say, 9 people walking together, the average IQ for that group is going to be between 70 and 90. So if we look at the formula, basically have to take the standard deviation and divide it by the square root of n. So what's the square root of 9? It's going to be 3. So if I flip this over, everything else here is going to be the same. What this is going to end up being equal to 15 divided by SQRT, and then I have to open parentheses, 9, close parentheses. SQRT in Excel language just means you're taking a square root. Now if I hit the enter button, you can see that the probability that you meet a group of, say, 9 people and their average IQ is between 70 and 90 is now 2.28%. I'm going to write this down real quick too. So 0.0228. So what we've got is if we're just looking at the average or talking about one person that we randomly meet, there's a probability here that you're going to meet someone with this lower IQ, about 23%. A group average that's between these two, 2.2%. So a whole lot smaller, which should make us feel a little bit better. But has anyone ever been walking down the street and you started talking with someone and you started to realize that maybe they're not that smart after all? Versus say you see a group of 9 people in this case that are walking down the street and the whole group seems like it's a bit below average intelligence wise. Anyone ever have that experience before? Yeah. So anyway, we can make a joke about it, but we can actually look at these things and try and figure out what are the odds of, or what's the probability of these things happening. And just so we can see kind of what's going on here. So 70 x 90 when n equals 1 versus n equals 9. So this is 0.2297. This is 0.0228. If I change the range of values, so instead of a 70 to 90, I'm now looking at 90 to 110. So we've still got this 20-point range we're dealing with. And if I look at it in terms of n equals 1 versus n equals 9, flip back over here. So this time the low value is going to be 90, the high value is going to be 110. Because I've already got this set up here, this is actually going to be the probability that if you see a group of 9 people walking down the street, they're going to be of about average intelligence. If we're looking at just one person that's walking down the street, so that's 0.495. So what's going on here is essentially this becomes n equals 1. This thing here becomes basically n equals 9. Because we're looking at the average of 9 people, that's going to make the standard not necessarily the standard deviation, but that standard error. So divided by the square root of n thing. The width that you have to worry about is a lot smaller. Some of the things where this comes up, I know for you guys, might not be a thing that you need to worry about. But if any of you are thinking about getting into, say, safety engineering, when it comes to the plant that you work at, you need to worry about, say, what are the average or how the average person is going to respond to whatever is going on. If you're going to have a lot of people that are exposed to things in a particular plant, you need to know what's going to happen to those people as a group on average, which is what we're kind of looking at here. If we're looking at, say, what is the speed limit of the road out in front of your house? And the posted speed limit, not necessarily the speed limit that people actually drive. One of the reasons why it is what it is because like Michigan State Troopers, they tend to be the ones that come out and do these calculations. They look at the average speed of cars in the area. They look at the average or the number of cars that are coming through that particular area. Then they look at like the number of, say, accidents, both major and minor, put all this stuff into a formula, and then the formula basically spits out a what essentially what the speed limit should be. So depending on the area you're in, a lot of times the speed limit hasn't been changed in 20 or 30 years. And because braking distances have gotten a lot better in vehicles over the last, say, 40 or 50 years, that essentially means you can actually drive faster and still be just as safe as you were before based on how well your brakes work. So there have actually been some cases where, and if any of you have ever felt this way, say we're talking about not necessarily the residential road that you live on. Well, let's say the first main road that you go to once you get out of, say, your apartment complex or you get out of the neighborhood that you live in. What's the speed limit on there? How fast do those people actually drive? And do they seem to you like they're driving like maniacs or idiots? I know a lot of people think that way. So there's actually been some petitions put out to, say, change the speed limit. And one of the weird things about that speed limit, because like I said, it's based on how fast people are going, how many people are driving in the area, how many accidents there have been in that area, and like major and minor accidents and stuff like that. And it also deals with braking distance of vehicles. We can actually get to a point now where, say, the road that's out, or the main roads right by my house, they tend to be 35 miles per hour. If they redid the calculations for that, they'd probably actually be increased to like 40 or 45 miles an hour. even though there's a high school half mile that way, there's an elementary school half mile out that way, and the middle school I went to was 3/4 of a mile over that way. So you've got all these school kids walking around because people have better brakes. They can actually stop in shorter distances because they can stop in shorter distances. It's safer for them to go faster, which is completely against what a lot of people actually want to do with these, which I know is really, really weird, right? So when it comes to making some considerations like that, we'll I'll actually try to do a calculation real quick just to show or see what's going on here. Let's say it's known that safe stopping distance on a particular road, let's say if we're talking about a road in front of a uh, say like an elementary school or a middle school or something like that. Let's say we know that that stopping distance has to be 50 feet. If we, when we look at the data, if we're talking about some of the older cars, and just out of curiosity, did any of you get a chance to go to what is it, Back to the Bricks or Hit the Bricks this year in August? All right. So anyway, let's say we need the safe stopping distance to be 50 feet, and we need, say, 95% of all the vehicles to say stop 50 feet or shorter using the calculation for the Z value here. I believe on this one it's going to be like 1.68. Oops. Sorry. That's uh, it's happening again. Because we're only looking at the one uh so any one vehicle at a time. Let's say we know that at 30 miles per hour, mu is, let's say, 30 feet. At 40 miles per hour, mu is going to be, I don't know, let's just make this kind of symmetric or kind of follow each other. 40 feet. So the faster you're going, the longer it takes you to stop. That sounds reasonable, right? We can actually go in there, figure out this value here. Sorry, this first time I'm trying to do a problem like this. So I'm getting way, way, way ahead of myself. Let's say in the olden days, this was 20 feet. Newer vehicles, that sigma is only 10. Okay. So what we can do is we know that we need 95% of the vehicles to stop in a distance of 50 feet or less. So this value out here is going to be 50 feet. And then we can relate the X bar here back to some of these values that we know to try to figure out, or once we have this value, sorry. So that's going to be 50 feet. Sorry, we need to find the mu there. We do that over 20. Work things around, figure out what this mu is going to be. And we can find out what the average stopping distance needs to be based on all of these different values. And my apologies, I'm getting myself lost on this right now. So let's forget I've mentioned that for the moment, okay? I don't know, maybe I just made a new toy for my cats. Anyway, I'll have to look into that a little bit better and have something for you next week. Anyway, coming back to IQ. So sorry about that. IQ on average is going to be 100. Standard deviation is going to be 15. The larger the group we're looking at, the narrower the range of values we're going to be finding if we're talking about average IQs for groups of people. Couple things that actually happen with IQ. Has anyone actually studied IQ before in any of your psychology classes? So I apologize for that. All right. So if we look at raw score, and I believe IQ started coming out like right around 1900, and let's say we're now looking at the year 2000. When you look at the raw score, hopefully everyone can see my little dots here. But at a certain time, say right around 1980, there's this really big jump. Anybody know what happened about 1980 that might cause people to seem like they're a whole lot smarter than they used to be?
Computers, technology, calculators.
Nope. With a lot of these IQ tests and all that, it's a test of what you can do, not what you can do with technology. So you're not necessarily going to be able to have a calculator with you. So if there's any math problems on there, it's going to be on you to do the math problem on your own. Anybody else want to have a guess what happens in the like late 70s, early 80s? It's a good guess you had.
Is it more people started going to college?
So it's not drugs and it's not people who started going to college. When it comes to IQ, the way that it's actually scored, whatever the average raw score is for that particular year becomes 100. And then there's also IQ is also based upon, say, age. So if you are, so you might have an IQ of say 120 when you're 5 years old. Well, when you're say 10 or 11, you might be seen as having an IQ of say 100 or something like that. So you're more average. But when you take all age into account, uh, IQ scores over the years have gone up and up and up. And no, it's not more people are being tested or taking, say, practice tests for the IQ test or whatever. Uh, anyone here, like, say, 50, 60, 70 years old? If you are, don't mention that you are. Or if you know someone that or is you can actually talk with them about it. What type of gas did all the old vehicles used to run on? If you go to a gas station now, what does it say the gas is that you're buying? It's diesel or what?
Ethanol gas?
Well, not necessarily ethanol. Uh, Lonnie just got it. Leaded. Leaded versus unleaded gas. So, uh, when you stop burning leaded gas and you start burning unleaded gas, there isn't as much lead in the atmosphere. There isn't as much lead deposition all over the place, which means you aren't ingesting, you aren't inhaling, you aren't consuming as much lead as you used to. What's one of the side effects of lead poisoning? One of the things is lowered IQ. There are some hormonal issues that come up with that too. Uh, there are some issues where people that have like higher lead concentrations tend to be a little bit more violent than they would be otherwise. Which unfortunately means if we're talking about Flint in the or the water crisis they had, some of it was because of improperly sanitized water. Some of it was because of the lead concentrations. And because of all the lead poisoning that a lot of the children had over that year and a half period, 2 year period, whatever it happened to have been, there's a chance that by the time they make it to, say, teenage years and adulthood, they're going to have more likely have learning disabilities, more likely going to have lower IQs than they would otherwise, and probably be a little bit more violent than they would be otherwise. Does that sound like a good future for the children of Flint? I don't think so. Um, but anyway, uh the with IQ, no matter what year it is we're dealing with, the average is always going to be 100. But some of the questions that have been asked initially with the IQ were actually put on there based on uh, ins- it was based on class. There'd be questions on there. So just a quick show of hands. Does anyone here own a boat of any kind? So one person. All right. So uh, some of the questions that would be on there would be, what are some of the different parts of your sailing yacht? Does anyone have a sailing yacht and know all the different parts of it? Back in the day, you're going to have the big pole in the middle that's called the mast. What's the right side of the yacht called? What's the left side of the yacht called? Why are they called that? What's the front of the boat called? What's the back of the boat called? I think the back is what, the keel, or is that the thing you put in the water to kind of uh, point the direction that you want to go? I don't even know. But if there'd also be, yeah, so starboard and port. What's the right side? What's the left side? I honestly don't know. So if we were taking this IQ test from back in like the 1900s, 1910s, uh, Abby's gonna kick my butt. So as time has gone on, it's gotten away from trying to show that uh, rich people are smarter, which is something that is in general actually true. But why are rich people smarter? Is it because they're rich, or is it because their wealth has given them opportunities that, say, some of us might not have had? Uh, an example of that how many of you actually have a graphing calculator versus scientific? One of the things I studied uh, several years ago was trying to figure out why certain students didn't do well in certain classes. And if we looked at it, the data, and we sorted people out by race, and you look at, and all you do is, so, uh, so if you look at the people by race, white people tended to do a lot better in these classes than Black, Latino, and what I had to designate as other because there's 12 different categories. But for the analysis, I would end up only having 4. And if you then look in white students were 70% chance of passing, everyone else was at like 20. But all of a sudden, or sorry, 15. But all of a sudden, if we look at poverty level, all the poor people, so all the people, or for the sample that we consider poor, uh, so students that are Pell eligible, I was, so not trying to throw shade at anyone. I was in that group for many years. Uh, students that were Pell eligible, it's 15%. Students that are not Pell eligible, were passing at like say 80 to 85%. So the achievement gap that we were looking at had nothing to do with necessarily what school you went to. It had more to do with did you have the right technology? I don't remember who I was talking to earlier in the semester, but one of you showed me that you had like your old scientific calculator, and I said that if Einstein was in this class and tried using a scientific calculator to do some of these calculations, he would actually fail it. Whereas someone that isn't very smart but has one of these would probably at least pass. So one of the things that I've done, I don't have them in here with me because they're still in my car, but I've actually got 20 or 25 graphing calculators for my students to use. One of the things that happens in all my classes where they're allowed to use calculators, all the students are at the same level, and all the students basically, or all my students tend to outperform other students. Uh, some of them kind of don't appreciate that until later on. And from looking at the data that a lot of you had, when you're looking at, say, the best professor versus the worst professor in some departments, wasn't there like 30% pass rate for the worst professor, say 80, 90% pass rate for the best? Or at least in some of the classes, that's what you found. So how do we help students do better? Uh, recognize that if you don't have a graphing calculator, bad things are going to happen to you, or it's not going to be as good. If you don't have a graphing calculator, do not buy one. The Excel sheet that I've given you for that says exam one calculator and the StatDisk website that I've shown a couple of times, those give you all the same answers as a graphing calculator, and they're free. So use your money on more important things like, uh, trying to buy uh, beer, whatever, after class. So do this one thing, or get back to this real quick. So anyway, so one other place uh, where we can use the Sigma, and hopefully this gets you a better idea about the use of a Sigma and stuff like that. So, stock market. And again, I'm not a good speller, and I'm not afraid to admit it. If we have some stocks that are volatile, so that's the term I was trying to think of earlier for high variability. And versus low volatility, so low variability. Just as an example, let's say we've got a couple of stocks we can look at. Both of these are going to be an average of 8% return. The high volatility stock, let's say a high volatility stock is going to be 6% standard deviation. The low volatility stock is going to be, say, 1% of volatility. It's a big difference between these two. And we want to look at this in terms of rate of returns. So I'm going to say 10% or more is honestly like great returns unless we happen to be dealing with who's the Ponzi scheme guy who went to jail a couple years ago.
Bernie Madoff.
Yeah. So if we have 6% to 10%, I'm going to say these returns are good. If we have, say, 4% to 6%, I'm going to say those returns are okay. 0% to 4%, you lose value of the money that you're trying to save and invest. Because if we think about how much prices are going up per year, so if we put that at say 4%, if you get a rate of return that's between 0 and less than inflation, you're losing value. The amount of money in your account goes up, but the value and the amount of stuff you can buy is diminished. And if it goes from, say, negative infinity percent to 0%, you are just outright losing cash. We can go in and we can look at all of these. So flip this over again. And this is basically what you guys have been looking at already. And I was actually showing one of my colleagues down at U of M Dearborn the same type of calculation. So the volatile stock versus, well, we'll call non-volatile. We want to look at what is the probability that with each one of these stocks you get 10% return or greater. So over here, put in the 8% return that we're looking at. If we're looking at the volatile stock, the standard deviation is going to be 6. Here, the low value we're looking at is going to be 10. The high value we're going to be looking at is whatever value we want. If I put in 200, if I put in 2000% return, not much is going to change here. So in this case, there is a 0.369% chance that you're going to have really great returns. With the non-volatile stock, change the standard deviation to 1. This brings us back down to that 0.02275. If I now want to look at a rate between 6 and 10%, so I'm not getting great returns, I'm just getting good returns. With the non-volatile stock, there's a 95.45% chance of getting good returns. With that volatile stock, there's only a 26% chance that you're going to get good returns. For now, going to be looking at okay returns, so 6% to 4%. Again, with this volatile stock, we get 0.11, going to call it 117. If we look at the non-volatile stock, again, we get 0.02272 instead of 75, so almost the same. Change this again for gaining monetary value but losing purchasing power for the non-volatile stock. 0.0004, so 32. Change that to the volatile stock. So there's a 16% chance, 16.1%. What are your chances of actually losing a lot of money? So 0 is now the high, the low here is going to be negative, infinity technically, but I'm just going to put in negative 1,000 for the volatile stock. 9% chance of you actually losing monetary value if we're looking at the non-volatile stock. 6.2 times 10 to the negative 16. So I know I went through that a bit quickly and I apologize for that. But if you look at the values that we've got here now, with the volatile stock, the chances that you're going to make Bernie Madoff returns is huge. With the non-volatile stock, the probability that you're going to make great returns is a possibility, but I wouldn't be banking on it. I wouldn't be thinking, I'm going to be in this category. Getting good returns, 26% for the volatile stock. For the non-volatile stock, it's going to be 95 or 95.5% of the time. You're going to get good returns. Okay returns, you can see the huge difference there. The probability that you could actually be losing value or purchasing power, and the probability that you're going to literally be losing money. It's now between these two. So again, if we're looking at all these different plans, which one would you rather be looking at? The non-volatile stock, where you're pretty much guaranteed to get good returns. Not going to be, or could be great, could be okay, but I'm fine with that as long as I'm making money and I'm increasing my ability to buy things and I'm increasing the value of the money that I have in these stocks. And if it allows me to sleep well at night knowing that I'm probably not going to lose money, that's good enough for me. For some people, they're going to go with the volatile stocks because they are more interested in the bigger chance of having really great returns. So with all this sort of stuff, we can look at it and we can like essentially go with whichever one of these you want. There honestly is no right answer or wrong answer to it. This is personal opinion. You may look at these people and say, well, there's a 9% chance that you're going to lose money and a 16% chance that the money you do earn isn't going to have the purchasing power you had before. Whereas I don't have to worry about that. But then they're going to say, well, there's a 36.9% chance I'm going to make a whole lot more money than you. Okay. If that's the way they want to play it, I am totally fine with that. One of the weird things that can happen as well is if you, has anyone here actually buy stocks or have any retirement savings? So a couple of you. I've got pretty much all the money I have in retirement is from the times that I was working at U of M in their environmental health science department as a research assistant. And I'm actually in this category right here. But one of the weird things is to be in this category where I'm pretty much guaranteed to get, say, good returns. I've actually got quite a few different volatile stocks, but as long as the stocks that I'm buying that are volatile, as long as their prices remain essentially independent of each other, they actually behave like non-volatile stocks. So this is the idea here of, say, 6% divided by square root of 1. Over here, this is 1% divided by the square root of 1. But I can actually approximate this with the more highly volatile stocks if I choose the right n value here. And in this particular case, if I invest in 36 different stocks that are all high volatility, it actually mimics the non-volatile stocks, which is weird. Is it a good plan for dealing with stocks? And this is part of the idea too, if you are going to be getting into the stock market and all that. This is what you would call a diversified portfolio. These would both be basically putting all of your eggs in one basket and hoping that you don't drop them. So when you hear people talking about returns with the stock market, this is what they're talking about. Volatility is essentially a larger standard deviation than a non-volatile stock. If you diversify your portfolio properly, uh, if one of your stocks goes down, what is the chances that all of your other stocks are going to go down? If everything is independent, you're going to have some stocks go down, you're going to have some stocks go up, but you're going to average whatever that happens to be, which is really, really weird. And I'm looking at it right now. It's 7. Let's do 10 minutes. And at 7:10, we'll do a little bit more with the normal distribution. And I will talk about the exponential distribution, which is actually kind of really, really useful for people that are in the medical field, which, if I'm not mistaken, most of you are in the medical field, right? So we'll get back to that. So who was asking about homework number 1?
I was.
Okay.
I just had, I sent you an email, but I don't know if you got it. I'm trying to pull it up right now so I can look at it, but one of the questions was, let me see, sorry.
No problem. By the way, I am trying to rewrite the rewritten uh lab that was based on something that I rewrote based off of something that I rewrote about rewriting the rewrite. So I'm still trying to rewrite it better. Haven't gotten to it yet,
Oh,
clearly.
okay. So one of the questions was how, wait, not that one. Oh, right here. For the pass rate, it was saying who has the highest pass A rate, and then it's talking about like difference between pass A rate and the second attempt. Um, but with the data we had, there
Pass it
was,
with the first attempt.
what was
Did
that?
I tell you to look at second attempt or?
Yeah, it said how much of a drop off is there between first and second attempt, but we can't see
Oh,
that in the data we got.
uh, yes, you can.
Oh, maybe I was looking
Uh,
at it wrong.
well, I'll just share my screen real quick. I have way too many files on here. Documents, not the transcripts. Was it down here? Well, I will do it this way. Go to assignments, lab number 1, download the OU data. So I'm already downloading it. Open that up. Enable editing. So highlight everything
Okay,
and go to insert.
insert.
Yeah. Come on. Yeah, so apparently if I have this two clumped together, it doesn't pop out. But then I can go to pivot table. Yes, I want a new or this to open up over here. Drag this down. So if we're interested in pass with an A, we need average. And then we need this to change over to count. So this is more like the data that you have. So right here it says overall 29% of students pass with an A. That's out of 137,738 student records.
Okay.
And so course name. So now you can see clearly you want to be taking computational chemistry here, right? Because 68% of the students get an A.
Mhm.
Or take a general chemistry 2 lab. Probably not. But if we want to look at attempt on top of all of this, I should be able to drag attempt down here. So just looking at algebra 1 here, 14.8, 14.9% of students get an A the first time they take it. 9.5% of students get an A the second time they take it. Oddly, 11% of students who take it a third time get an A. But here, looking again at for algebra 2, 14% of students pass it or pass with an A the first time they take it, 7% the
Oh,
second time, 3% the third time. And does anyone else feel really, really, really sorry for these people?
people who tried it 9 times and still didn't pass.
Well, this is so clearly this is like the exact same person who took it 9 times. There are 2 people that took it
Oh, that's
2
bad.
times, 3 people that took it 5 times, 23 people that took it 4 times. 147 people retook Algebra 2 3 times.
Okay, that helps. So you have average of pass A and count of pass. What's that count of pass A too?
It just happens to be like that because I grabbed Pass A, brought it down here, and then grabbed Pass A and brought it down here a second time.
Okay.
So it's average of pass, or the average number of students that pass with an A, and then the count of, or the number of students that pass with an A in each one of these classes.
Okay. Yeah, I think I was confused. I couldn't figure out how to decipher between the number of times people took it. So that helps. Thank you. I'll
Yeah,
just have
so
to, I'll unsubmit it and then resubmit it then.
problem there.
Okay.
Dear God, look at this person. They are persistent. 10 times. A lot of these are 3s and 4s. So one student took a class, differential equations 7 times. Dear God. So again, it looks like this person right here is very persistent. So that's intro to chemical principles. So if you're a nursing student, I believe you have to take, what is it, intro to chemical principles and then intro to organic and biochemistry. So this is the first one that you take. So
Thank you for
have all
showing me that.
yeah, no problem there. And I believe it was Verlin had a question about homework too.
Yes, I think it's homework 2, assignment 2, with the probability sheet. I wanted to know, how do you use the formula to get those answers? The formulas that you gave us?
Well, this is the sheet that you use. So I honestly don't remember all the values that I gave you to work with. But let's say, just as an example, that we decided that the false positive and false negative rate are going to be 5%. So those two numbers are already in there. And let's say the probability of someone has this disease is 3%. That's literally all the effort that you need to put into it. And then when I'm asking, what is the probability that a positive test is accurate? I can also put this in statistical terms and say, what is the probability that you have the disease given you just tested positive? So in this particular case, 37%.
Where's the 30? Oh, okay, I see it. Okay, got it. Okay, I think I got that. Now, up in H, you got 102. Where does those numbers come from? The $1,000, the $25, the
Well, these,
1,000? Uh-huh.
depending on what class I'm teaching. So I think we got some time for it. Let's just say, for example, and this is something that could actually apply to anyone in the class. Suppose for a moment that you're going to be working at a clinic or a free clinic. Clearly, they're not going to have a lot of money to buy all these different types of tests and stuff like that.
Okay.
And for the way that this works here, what I am saying is that when you go to buy the screening test, whatever it happens to be, it's $25. The confirmation test here is $1,000. So this means anyone that tests positive has to come back in for the confirmation test. And then what we're looking at here is, so if we're, let's say for a mammogram, you're going to get a couple of x-rays. So the screening test is going to be, whoops, not 1,000. Well, let's say $100 because each x-ray comes out to be $50 or something like that. The confirmation test, let's say that's $5,000 because it is an invasive surgery type of a thing. And we know from what we were looking at that mammograms are somewhere between 90% accurate and 80 to 90% accurate. And let's say, because I don't remember, let's say 300 per 100,000 women in whatever category you deal with at that particular place have breast cancer. Based on all of this, the average amount of money you are spending on that particular or on anyone that comes into your clinic for a mammogram is going to be that $612.
Okay.
So let's say there's a new test that comes out. That new test is 95% accurate, but that new test also costs, say, $250 for each patient that you have. So in this case, the
Average
cost of
cost
the
is
screening
$550.
test is more, but the average cost per patient is now what, $100 less than it was? Let's say there's another test that comes out that is 99% accurate. But this particular test is, let's say, $400 per patient. So now we have the average cost per test for this medical clinic that you work at based on the cost of the screening test, the accuracy of the screening test, and essentially the cost of the confirmation test. So if you're taking the business stats 1 class, all of this stuff becomes really, really important, right?
Okay.
If you're looking for a way to save money, what are you going to vote for? Let's say you work for an insurance company, and the insurance company recognizes that mammograms are life-saving thing. But if you look at, again, at what we have here, this more expensive test to begin with, because the insurance company is essentially going to be paying for all of this, using the more expensive test that is more accurate is actually a lot cheaper for them than the other tests that we started off with. So 0.1, 0.1. What did I say the screening test was for the mammogram? $100. So
$612.
So if you are working for an insurance company and you know that your female patients are going to have breast screenings, do you want them getting the traditional mammogram? Again, based on the numbers I put in here, based on the numbers I put in here, are those the actual costs? I honestly have no clue at all. But just with my example here, would you rather the women go in and have the mammogram where you end up paying, say, $612 per woman versus this more accurate test to begin with. And even though it costs more to begin with, you end up saving what, about $150 per woman.
Mm-hmm.
And if you look at it from the insurance perspective, they're going to say, hey, no more mammograms. You need to start using this test. We will cover whatever this new test is. And if you think about it too, for the women that are taking it, the accuracy of a positive test based on this is 22.95. So 23% of women that are told by their doctor, we found an anomaly, we need you to come in for further testing, will actually uh, have their, or it will be cancer, and then they can get the treatment. You look up here, the number of women that will be told they're fine, but they have cancer is only 3, versus uh, this other test. And again, I'm making these numbers up. But now all of a sudden, with a traditional mammogram, 30 women are going to have breast cancer and not know it and be told that they're fine. And when you look at the accuracy of the positive test here, uh, you're going to be scaring the crap out of 97% of the women. Does that sound right? If you're a woman and
Where
you're going to be getting a mammogram,
Mhm.
with, for this type of so the mammogram here, we've got 2.6% of women that are told, we found an anomaly. We need you to come back in for further testing. So you're scaring the crap out of 97 to 98% of women, versus, uh, and you're also not catching as much.
Okay.
So it's like on a personal note here, that's where this sort of stuff comes in. If you're the insurance company, you want the better test.
Right.
Uh, if you're a woman, I would assume you'd want the better test as well, because there's less chance that someone's going to scare the crap out of you. There's less chance that you're going to be told you're fine and you have breast cancer. So in this case, it just ends up being better all around to use the better test that I've made up for this. Does
Okay.
that make sense?
It makes sense. I think I got it.
Okay. Yeah,
Thank you.
so
Thank
there's a
you.
lot of stuff that's going on here. But anyway, and for those of you that just came back, hopefully you caught a bit of that as well. Let's see. Gonna make these go away. Now, one of the other things that we need to look at, and this is hopefully another really good example of uh, how variance can affect things. Let's say we've got 2 different experiments that are going on here. One of these has very small variability. One of these has very large variability. Okay. Here, I'm just going to say that the average is 20. Here, I'm going to say the average is like 3. I'm going to say if we come out 2 sigma in each direction, on this one, we're going to be all the way up here at 35, all the way down here at 5. So for this, our confidence interval is going to be 5 to 35. Let's say on this one, from here to here, again, that's going to be 2 standard deviations. Coming back from here to here, again, that's going to be -2 standard deviations. But let's say that's going to be 4, and that's going to be 2. So our confidence interval here is 2 to 4. Our confidence interval up here is going to be 5 to 35. Okay. Now, when we look at these, the confidence interval is the average plus and minus the margin of error. Margin of error is going to be approximately 2 times what I'm going to call the standard error. This actually has many formulas. So many formulae. So I'm not going to worry about all those different values. I'm just going to take this as the whole here. So looking at the data here, we need to figure out what is X bar, what is the margin of error, and what is the standard error for all of these. And I will tell you right now, there is exam problems based on these calculations. And we will do some more of these next time. The formulas that I would use to get all of these. This is the upper confidence limit. This is the lower confidence limit. And with these confidence intervals, it's just like we were talking about before. This is the range of values we would expect to see from this population versus this is the range of values we think we would see versus this population. To figure out the average here, we take the UCL plus the LCL and divide it by 2. I already said here that it was 20. So we kind of know what that's going to be. But 35 plus 5 is 40. 40 divided by 2 is 20. Down here, so this is technically, down here, we already know that this is going to be 3. But this is basically going to be 4 plus 2 divided by 2. So 3. The margin of error is going to be this upper confidence level minus X bar. So in this case, 4 minus 3. Up here, 35 minus 20. So here we have 15. Here we have 1. Standard error, because of this, is that margin of error divided by 2. Down here, this is the margin of error divided by 2. So this is going to be 1 over 2. This is going to be 15 over 2. So 7.5. And with the normal distribution and with a lot of the experiments that any of you are actually going to be dealing with, some of the assumptions you have are that if you're doing an experiment on a population and you grab a sample from that population, the standard deviation or the standard deviation is going to be the same for everyone that works with this population, which means the standard error is going to be the same. If assuming that they have the same number of people, the margin of error is going to be approximately the same thing. What's really going to change when, say, I do an experiment versus any of you doing an experiment should really only be these averages, okay? So we were saying up here, because of the much larger standard error, standard deviation, we expect the results to be somewhere between 5 and 35. Down here, we expect the results to be somewhere between 2 and 4. And what we can do with this, because these confidence intervals do not contain 0, we believe that whatever it is we're studying has a positive impact on both of these. If both of these values were negative, then we could say we believe it has a negative impact. We'll see sometimes a negative value just means not necessarily negative impact, but just the way the calculator does the calculation. But we can say here we believe there's a positive impact, here we believe there's a positive impact. We can then go to a journal or go to our computer, write a journal article and say, hey, under where we just studied this population, we found that there was this positive impact here or this positive impact down here. And the big thing that we're looking at here is probability in the case of what we're looking at. Others also find a positive impact. We're going to later come out and say this is actually a statistically significant difference. So for both of these, what we need is over here, we're going to have X bar equals 3, margin of error equals 1, standard error equals 1/2, or we can say 0.5. And to have, or for other people to find that we have a statistically significant difference. So this is a conclusion that people draw to say, hey, it looks like there truly is a positive impact here. What are the chances that others will do this? So looking at this bottom one, looking at this top one, so X bar is 20, margin of error is what, 15, standard error is 7.5. So coming back to the exam calculator, and again, this is something that will be on the first exam. It also will be on the final exam. So if I click on the normal distribution, for that top one, my average is 20. My standard error, standard deviation is 7.5. The high value I'm going to look at is technically positive infinity, but if I just put in there 10,000, that's good enough. The low value is going to be my margin of error. And the value that we get right here is if someone comes in and tries to reproduce our results, approximately 74.8% of the time, others will come to our same conclusion that, yeah, hey, yeah, you did find something that has a truly positive impact. So about 1 in 4 articles or 1 in 4 people that come back and try to do your research will say, hey, I didn't see a difference here. And then you can start to have a discussion about that. If I do this for the other group or the other experiment, the average is 3. The standard deviation is 0.5. The low value here is that margin of error, so that's going to be 1. This other experiment, the probability that others who reproduce or try to redo the experiment find that there is or come to my same conclusion that there is a statistically significant difference going on here, is 99.997. So let's say you are, again, working for a hospital of some kind, and one of your patients comes in and says, "Hey, I just saw this article. It looks like by doing whatever we have in this article, my value for whatever this is will go up by somewhere between 5 and 35. Well, based on what we have here, only 74.8 or 75% of people that replicate this experiment will agree that, yeah, there is a positive impact on this. So there's a 75% chance that it's going to have other people will find it has a positive impact. Is that good enough for you? Down here, this one's 99.997% chance that it's going to have a positive impact on you. So between the two of those, so again, A versus B, which study do you believe more? The one where 99.997% of people that reproduce the results will say, or reproduce the experiment will say, hey, their conclusion that there is a positive impact here is true, versus this other study where only 74.8% of people that reproduce the study is going to say that it's true. So between these two here, would you rather believe study A or study B? Which one seems more trustworthy to you? Yeah. Yeah. The more people that study this, essentially, most of them are going to come out and say, hey, this group did a really good job. 1 in 4 people that look at this study are going to, or 3 out of 4 people are going to look at this study and say, hey, you did a really good job. Thing that you need to take into account, though, is what are these studies actually dealing with? If, say, we're talking about a diet, and a diet that does no harm, or essentially does no harm to any person, and there's a 75% chance that you could lose or lose weight on this diet, for a diet, is that good enough? If this is a brand new, say, cancer treatment that is, say, highly toxic, highly painful for the patient to endure, is 74 or 75% of people will say, hey, we think they got it right. Is that good enough in that case? And I would say no. So again, when we're looking at these, once we have the information, we can then start talking about, do we trust it? Would we do it to ourselves if we needed to? And again, are we willing to do it to ourselves should be dependent upon what percent of people are likely to come to the same conclusion, which is that there is, say, a positive impact going on here. And also, what are we actually dealing with? And who knows? If there's actual chances here that, say this new study where 75% of people that reproduce or uh, do this experiment will come to the same conclusion that there's a positive outcome. Sure. Well, you don't want to see this ugly face anymore? Fine. So, again, if this particular study or this new study has 75% of people are likely uh, to be able to reproduce the results. And let's say there was another study, or there was a study done a while back on the same type of procedure, but when you go and you do these types of calculations over again, you look at this value here, and it's say 53% of people uh, that try to reproduce the experiment will conclude that there is a statistically significant difference here, meaning that there is an actual positive impact happening. So if I have a choice between the 75% one versus a 53%, I'm going to take this one all day because there's a better chance that it's actually going to be helpful. So with all these numbers, we always need to put them into context. And just in case any of you need to know the formula, and like I said, this is going to be on the exam. Yeah, go ahead, Abby.
I am confused. So you use the exam calculator to find the probability.
Mhm.
But when I'm putting it in, I'm getting 95% for both of them. I don't know if I'm putting my numbers in wrong or what.
Well, how about we look at or I'll write down the formula and try to
Oh,
make it really clear what's going on here. And then we'll go from
okay.
there.
Okay.
So whatever the two values are, the average that we're going to look for is the smaller value plus the larger value divided by 2. The margin of error is going to be the larger value minus x bar. Standard error is going to be margin of error divided by 2. So if I have this, and I will say this right here is based on a 95% confidence interval. If it's a 90% confidence interval, this number goes down. If it's a 99% confidence interval, this number actually goes up. But for what we're doing, I'm going to assume the 95%. So if you look at on the table, I've got average, standard deviation, x high, and then x low. If you put in there that x bar, that standard error, and then whatever the b value is here, and the a value is down here, that's going to give you the 95%. That doesn't belong there. That doesn't belong there. What it should be, again, is average, standard deviation. X high is technically infinity. Good luck typing infinity into there. So we're just going to say I can put it near 10,000. X on the low value, that's actually going to be the margin of error. So just to do this with one more data set, again, let's say our results show that the confidence interval is between 10 and 20 with X bar using the formula 10 plus 20 divided by 2, 10 plus 20, 30 divided by 2, 30 divided by 2 is going to be 15. Margin of error is going to be the larger value here. So 20 minus the average, 15. So that's going to be 5. The standard error is going to be 5 divided by 2. So that's going to be 2.5. So when I go to put these numbers in there, I'm going to have 15 here, 2.5, 10,000, and then 5. If you put those into the normal calculator that I've showed you, I'm going to share the screen real quick. So if I just put them in that order, 15, 2.5, so 10,000, that's already there. The low value here is going to be 5. So here again, we've got the 99.997%. So completely different numbers than what I did up here. But essentially because of the size of the margin of error, it's a value that is not in the confidence interval. So there's a really good chance that if someone else tries to run this experiment, they're also going to find that there is a statistically significant difference between the groups. And Abby, when you're putting the numbers in the way that I've got them in here, are you getting the 99 or
Yeah.
0.9997? Okay.
Yeah, I just had the X high. I didn't know it was supposed to go in for that. So yeah, thank you.
Yeah, no problem there. So again, these are just a bunch of different examples. And you can see where everything goes in. And in case you need to copy down the formulas, so the high value that we have here, the 10,000 that I put in there, that generally works out really, really well. The thing that you need to do, the thing that you need to remember to do anyway, is you need to remember that the high value has to be a lot larger number than the average or the standard deviation. Doesn't necessarily need to be 10,000. If I flip this over real quick to share my exam calculator here. So you can see what this value is when I say the high value is 10,000. What if I make it only 100? This didn't even flinch. This didn't even come close to shade changing. If I make this 50, what happens? Because 50 is so much larger than 15 and so much larger than the 2.5, again, nothing happened here. What if I make this 25? Now I got a change over here. So 25 is not that much larger than 15 and not larger or really, really large compared to 2.5. So in this case, I would feel completely fine doing it with, say, 100. Now, let's say you're doing this for future work, okay? Let's say that you find that the average person weighs 160 pounds. The standard deviation for that is, say, 40 pounds or something like that. X high of 100 is not going to be anywhere near enough. We might actually, in this case, bring it up to 1,000. And then the low value here is whatever your value of interest is. So for what we're doing, I'm going to zoom this out real quick, is so I'm just going to draw two of these generically. So going from here, -2 sigma, then out to here, 2 sigma. This is going to be basically the 95% confidence interval. What I'm having you calculate, again, if we think of the average here as 0, some value out here, that is the margin of error and everything on the other side of it. So up here, this would be all the shaded in area. If you look at some of the stuff they do online, some of the stuff that SPSS will come up with, they try to shade it in. Up here, we're looking at all of this area. So we're looking for this value in greater. If we have specified values that we want to look at, then we can plug those two values in, whatever they happen to be, and we can go from there. But these are the results. So if I ask you, what's the probability someone reproduces the experiment and their results confirm our results? It's whatever that confidence interval is. Down here, we're looking at the conclusion. So what is the probability someone will confirm our conclusion? It's the probability that X, so some whatever value they find, is greater than the margin of error. So as we've seen, if I have a 95% confidence interval, probability they reproduce my results should be 95% of the time. However, my conclusion with the one data set that we just looked at, it's 75%. With a couple of the other ones, it's 99.997%. You never know what this is going to be until you do that calculation. And again, that calculation when you put it into the calculator. That's basically going to be what we look for. Okay. Does that make sense? So what we're doing here is, do we trust the conclusion? And that's going to be a value that you are something that you need to be aware of and you need to be dealing with. I'll get you in a second, Brooke. So again, if we're looking at this, and in the case of, say, the new study, it's 75% of people will trust the conclusion. In the old study, 62% of the people trust the conclusion. I'm going to go with the results from the new study. If someone's trying to sell me some product, say like a new medication or something like that, and there's a 75% chance that other researchers will find it has a positive outcome on patient or on the patient, am I necessarily going to switch to that product? Even though in the case of what we were looking at here, showed that there should be somewhere between a 5 to 35 point increase uh, in whatever this is. So if we're talking about, if I'm thinking about my mom in this case, when she was in the hospital and she was actually dying from cancer, this might be on average, a new medication will give her 20 more uh, pain relief points. The medication overall should give her somewhere between 5 and 35 pain relief points. But if only 75% of people that experimented with this thing saw that there was a positive pain relief with it, if you know anyone that's ever been in cancer or had cancer, it's really, really painful, especially the last few years or the last few months that they're living. There's a 75% chance it's going to be good or help my mom. Is that good enough for me? Well, again, if the new medication is 75% and the old medication is only 62%, all right, give her the new stuff. But if I have something that's probably going to give her the pain relief she needs versus something that's definitely going to give her the pain relief she needs, I would say give her the medication that's definitely going to give her the pain relief she needs. Does that make sense? And Brooke, you had a question?
My question was more in regards to tests. When we have tests, will our bell graphs, will we get like example bell graphs that look like this that give us our A and B? Or, and if they don't, how would we figure that out? Or that might be a later question, but
Well, if you want to know, I'm not going to give you the exact numbers, um, but just essentially, a medication was tested and it found that it gave between or the 95% confidence interval for pain relief or increase in pain relief was 10 to 20. What is the average pain relief that a patient can expect? What is the margin of error based upon the study? What is the standard error based upon this information? What is the probability that when uh, other people start using this medication or experimenting with this medication, they are also going to find that there is a positive pain relief for their patients. So everything that we just did here, and then probability of conclusions. So this is literally the way one of these exam problems is going to work.
Okay, thank you.
Okay.
That makes a lot of sense. I just wanted to like double check and double make sure I'm
Yeah.
on the same
No
page.
problem. And my other cat has decided to join us at the very end of class.
Can we see him?
I don't know. Let's see. With this particular cat, I actually picked him up. He was roaming around in the mean streets of, and there he goes. The mean streets of Dearborn. He beams.
Oh my goodness, he's so cute.
He's also quite a bit of a terror for the other cat I was showing you. Uh, he thinks he's the alpha kitty, and all the other cats are like, well, he likes to fight, uh, but the other cat has 4 or 5 pounds on him. And when you compare the two, uh, the orange cat is like, say, that big. The other cat's like that big. So you've got essentially the heavyweight boxer going up against the middleweight boxer, welterweight boxer, whatever it is, and the welterweight's like, yeah, I'm gonna beat you, I'm gonna beat you, I'm gonna beat you. Yeah, he gets some good licks in, but he never is able to really become that alpha kitty that he thinks he is. But he loves to snuggle at night, sometimes in annoying ways. But anyway, one last thing to just show you, and we'll do more with the exponential distribution next week. But with, oops, I don't want to do that. But just really quickly, with the exponential distribution, what we have is, say, if we're looking at time versus, let's say, concentration of some medication. It'll start out at a certain value, and then as time goes on, it'll decrease, but it'll end up looking something kind of like this. If we think about nuclear decay, that's kind of what this is. The concentration of a medication that's in your blood after getting, say, the first dose is going to give you the same type of thing. This never goes all the way down to a concentration of 0. And if you've ever taken a chemistry class, we can think of this as C naught. So you get this one dose of the medication after a certain amount of time. It's going to be it's going to be really small. It never actually factually goes to 0. No matter how long you live, there's always going to be at least a few molecules of this stuff still circulating in your blood. And when we're talking about medications, the big things that we need to worry about are uh, I'm I'm just gonna call this uh sorry. No effects. It's with any medication. And honestly, if in anything that we consume. So technically, I'm assuming that at one point we were all babies. some of the formula we had when we were 6 months old is still, because of this idea circulating around in our body, it's still going to be in there. But if we're talking about medications, we need to talk about a dose where it's so level or so low that it's not going to have the desired effect. And then there's going to be another value up here where it's going to be a toxic. So when you start with the dose, essentially what you want to do is you want to keep it above the no effects level, but below the toxic level. And one of the nice things that you can do here is you can actually create this type of a graph by looking at, say, what is the concentration of the med, and I'm just putting numbers in here, or actually not putting numbers in here. So time 1, time 2, time 3. What you end up doing is you have the formula that we all had, I believe, in Gen Chem 1, maybe Gen Chem 2. This was for the amount of chemical that was still left over to be reacted and all that. But this is, say, a value that's going to be based on your particular metabolism. Once we have all this information, we can figure out what is the time to redose a patient. We can look at how much we need to give them to get them back to a value that is effective. So it should say from here out to here is the effective range. Keep them on the medication, give them enough medication so that it's having the desired effect. So again, if we're talking about, say, what happened with my mom in her the last couple months of her life, she was taking some really, really potent pain medications. And if we figured out what this was, I could actually, so let's just say, for example, for my mom, this value here turns out to be 5 hours after the dose. If we know what this value is, every 5 hours, we can give her some more of the medication. It'll come down. 5 hours later, more of the medication, it'll come down. And if we are able to do that and keep up with that, essentially my mom would not be in any pain. The problem is if we give her another dose too soon, she's going to get close to the toxic level. And then she might actually go into the toxic level and even further into the toxic level. And if she's taking something like morphine, which I think was one of the medications she was on, if we give her the medication too soon, she could actually die from an overdose. If we wait too long, from say this time to whenever we give it to her again, she's going to be in a lot of pain. So understanding the exponential distribution from a medical point of view, really, really important. We'll talk more about it next time. Understanding the exponential distribution in terms of the Flint water crisis. Now, I'll get you in second app. If we were to look at the data, and we will actually do this, if we plot the data, so we've got concentration versus the number of samples. what ends up happening is we have a value up here. And then out here, we have a value that's a 104. So this is 0. Most of the values are within this range. What ended up happening is the scientists that looked at the data, they figured out what standard deviation or what the average was. They figured out what the standard deviation was, and then looked at this data point out here. And if we assume the normal distribution, the probability that this 104 sample is true and not just some mistake, not random or not random chance or anything like that, is I believe 1 in 100. So that's 100 million, 100 billion. So the scientist actually kicked that value out. And that's part of what happened with the Flint water crisis. And one of the reasons why initially, when people were coming in and showing the bottles of like yellow and brownish water and all that, and are talking about how horrible the taste of the water was and everything else, they weren't believed, uh, literally because the scientists and engineers that were looking at the data made an assumption. Their assumption was completely wrong, but they didn't change their assumption because they never plotted the data. Since they never plotted the data, they're under the belief that, oh, there's a 1 in 100 billion chance that this person's correct. So we just think they're not necessarily we think that they're crazy, but we're not going to take their complaint as seriously as some other people. And how many of you were actually in Flint and in and around Flint at the time when that was happening? So for those of you that were, uh, there's a lot of mistrust by the people of Flint on the scientists. There's a lot of I know that there were a lot of people that thought the people of Flint weren't being listened to because of racism or something like that. And in truth, and at least with the data side of things, uh, the truth is the scientists weren't believing the people of Flint because the scientists did a bad job with the data. Had they done the right thing in the first place, and I'll actually do these calculations right in front of you. And they're not going to be calculations we do with pencil or paper. They're all going to be calculations we do uh, with the Excel. And quite literally, 20 minutes doing the right thing could have saved the people of Flint. I think it was between 9 months to 15 months of being poisoned. Unfortunately, the people of Flint would have still been poisoned, but it would have been 3 months of poisoning instead of, say, a year and a half to 2 years or however long it actually went on for. And all of that because someone didn't know what they were doing, but they were the one in charge, so they did what they thought they should. Horrible to think about, um, but it's basically what happened. So was it who had the question?
It was me.
All right.
I was
So
just
what
trying
was
to
your
I was just trying to make a connection so that graph you made with the medication dose and blood, is
Mhm.
that like what they doctors use when you're getting prescribed, like let's say I don't know, medicine for an earache, and it's like take one every or take one twice a day, one in the morning, one in the evening. Is that what they use to define that?
So I'm just going by the name that I see on the screen, and I'm seeing Abby. I'm gonna assume that you're female.
Yeah.
If you get into some of the research that's done on different types of medications, a lot of the research and therefore a lot of the dosing recommendations are actually based upon the average man.
Uh-huh.
So the average 160-pound man. And I'm assuming you're not a 160-pound man.
No,
So,
no, I'm not.
yeah. So when you look at those, or when you look at the, uh, I wish I don't have any here now, but if you look at the backside of the Benadryl, if you
Uh-huh.
get the stuff that's behind the counter at the pharmacy, you'll see that it says something like take 2 to 3 pills every 4 to 6 hours as needed.
Mm-hmm.
Reason it's so vague like that is, again, I'm assuming you're not a 160-pound man. I'm just going to fully volunteer. I am not a 160-pound man. I weigh a lot more than that. So because of that, I should probably take 3 to get the same benefit
Mm-hmm.
of, say, a 160-pound man taking 2. Whereas if you take 2 because you're not, say, a 160-pound man, and I have no idea how much you weigh, well, you may take 2 of those and have all sorts of weird side effects. So you might actually be getting into that toxic range.
Mm-hmm.
So for you, you might only want to do, uh, say, 1.5 pills every
Mm-hmm.
4 hours, whereas I want to do 3 pills every, or sorry, you'll do 1.5 pills every 6 hours. I'll do 3 pills every 4 hours, and we'll both receive the same type of benefit from it.
Okay. Okay.
So,
That makes sense. Thank you.
and part of the reason why it's done primarily on men and not on women is because there was a chemical or a medication that was actually given to pregnant women. I believe it was called thalidomide. If you look up what thalidomide does, um, I don't know what your personal plans are for the future, whether or not you plan on having kids or not, but the medication that they were giving to women who were already pregnant and had, say, morning sickness, it was getting into the blood of the pregnant woman, and she wasn't feeling sick anymore. The outcome of it, though, is it and it sounds derogatory, and I have no idea what a better term is for it, but I believe they were called flipper babies because if you look at your hands, you can see that they're the individual fingers and there's nothing in between them. And with these babies of mothers who took thalidomide, there's the webbing, kind of like you would see on a frog's flipper. And there were some other uh, abnormalities with babies that were born to mothers who took thalidomide. Because of that, they now, and if you watch a lot of the medications that they talk about on TV, they say ask your doctor about whatever, and make sure you tell them if you plan on getting pregnant or if you are pregnant. The reason for that is no one wants the deep child deformed children being born if we can prevent it. So what I'm proposing with the thing that I drew is say you're in the hospital, you're having some major issue, and it's a substance that may have like a really low value where it starts to get toxic. Um, the doctor can go in, see how much of the medication is in your blood, and say 2 or 3 different data points. Assume that concentration is exponential, like we just looked at, and then come up with, say, what is the perfect dosing regimen for you in particular. So it's not dosing based on a 160-pound man, it's dosing based on you. Does that make sense?
Yes,
Okay.
it does.
So yeah, with the exponential distribution as well, if any of you do get into toxicology studies, the exponential distribution is used in toxicology studies because you can use it for determining lifetime or looking at how long something lives after you give it a certain dose of a medication or a chemical, which unfortunately is the type of study that I was dealing with. If you get into engineering, or if you happen to be, like, say, you go and you buy a new 4-pack of AA batteries to put into your TV remote, and you find that after 2 months, one of the batteries already seems dead, but the other one seems perfectly fine. Uh, we can look at the lifetime of those batteries, even if they're all manufactured perfectly well, to the same standard. We can see how long those batteries are going to last over a given amount of time. And some of the stuff that we want to do is, if we're talking about, uh, say, a battery that someone's going to get put in case they have like a pacemaker or something like that. You don't want, or you want to try to make sure that the battery that you put in there, uh, eventually it is going to fail, but you want to try to make sure that the battery that you put in there, say, might not fail for 5 or 6 years, but then you're going to come up with a plan to, say, replace it every 3 years. Why do you replace it every 3 years if on average it's going to go for 6 or 7 years before it actually breaks? It's because you don't want the battery to stop working and then the pacemaker doesn't work anymore. Depending on the patient you have, if their pacemaker stops working, they could die. If you have a patient that needs like a pacemaker just in case their heart starts racing too quickly, in a case like that, if the battery goes bad, uh, it's not going to be something that's in constant use, hopefully anyway. So it might be a little bit safer for them. But still, you're still going to have surgery, pull the old battery out, put the new battery in. Any surgery you have, there's going to be risk. There's going to be risk of infection. There's going to be risk that, say, a doctor makes mistakes. There's going to be all these other risks that we need to worry about. Okay. And the way that we figure out, is it normal for, say, that battery that goes into your remote control to die after 3 months? And say the other one lasts 7 months, then you put in some other ones and they last between 6 and 7 months. Is that first battery you had just a bad one, or is it part of this exponential distribution? And it's actually part of the exponential distribution. So, and I know that I've said a lot, and I can also feel it in my throat too. So, if any of you have any other questions, feel free to stick around if you're already tired of listening to me talk. Have a great evening.
Thank you. Have a good night.
Talk to you guys next week.
Thank you. Have a good night. We liked seeing your cats.
Yeah. Sometimes they're nice. Sometimes they're, especially the older one and the fatter one, he will get really, really demandy. So he was pretty good tonight. So I appreciate that out of him. So maybe I'll give him some treats for being a good kitty tonight.
Yes. Treats from the class. Yes.
See you later.
I had a question before I go.
Sure.
So I see for the homework that's due tonight, question 4 refers to the accuracy of a urine test. Is there a resource that I'm missing with that information on it, or am I jumping the
It's
gun on
called
something?
Google.
Oh, okay, perfect. That works.
So, just so you know where this sort of thing is going along, there's the story that I have in there that actually happened to one of my students, uh, 2 winters ago, I think.
Okay.
Um, but the like the first journal article or the journal report that you're going to do is essentially you pick a disease that's of interest to you. You do not need to tell me what that disease is or what that medical condition is. If you want to say, uh, I'm interested in breast cancer because breast cancer runs in my mom or on my mom's side of the family or something like that, fine. But you do not need to say the reason why you're interested in it. Just need to talk about the medical or whatever medical condition it is. Are we talking about cancer? Are we talking about drug tests? Whatever it happens to be. You go out, you research how well does the screening test, so the initial test that a doctor is going to give to a patient, how accurate is that? So if you want to do, say, colorectal cancer, you could look up, say, Cologuard and see how accurate is Cologuard. And then you put that information into the calculator. You look up what percent of people you happen to be interested in. Um, I don't know how old you are, but let's say you're 23, 24, and let's say your dad is in his late 50s, early 60s, something like that. So that didn't need to know the age, but I'm just saying, let's say they are that old and you are concerned about them getting or having colorectal cancer. Okay. And again, you don't need to explain why you're choosing any of this stuff because that literally is privileged medical information. Uh, you you do what is best for you or of interest to you, and then you can put the numbers in there, and then you can come up with if your dad takes Cologuard in this situation, and let's say it comes back negative, what's the probability your dad does not have colorectal cancer? If if it comes back positive, what are the chances that your dad does have colorectal cancer? So
Okay.
that's where this is
I see.
coming from. Okay?
Okay. Yeah, that helps me out with the journal because that was my next question.
Yeah.
Okay. Thank you.
Yeah. So it's all on you. It's all whatever you are interested in. And again, and I'm saying this for you as well as for all the students that are going to watch this later. I do not need to know why you chose what you chose. If you want to tell us why, totally fine. Um, it's your choice trying to make it something that's interesting to you. And if I'm going to be completely honest, I have very little way of I'm really trying to figure out if you got the right answers or not, unless I start spot checking everyone and reading through all the different articles that you did. And dear God, that's going to take a while. So
Okay. All right.
I'm trusting you to be interested in something that's of interest to you
Okay.
and not try to come up with things.
Okay. Perfect. Thank you so
Right?
much.
Yeah, no problem.
You have a good night.
See you next week.